either way, so what is the rate that I need to earn to reach my target? It's not very different. Data, what if analysis, goal seek, make my difference zero by changing the thing that I don't know. Well, it turns out 0.91 is good enough. I mean, that's roughly times 12, 11% a year. A little bit bigger than small cap will do it for you. Yeah, if all you want is 3 million, .77. That's about 9%. Mid cap is cap, half mid cap, half large. Sorry, does it get to that? So basically, I determine what sort of risks I need to take. Again, did I have to go through all sorts of algebra? No. Math is about reducing the problem to things you know how to do. In this class, when it comes to time value of the money, you're going to know two things. How to calculate present value of an annuity with a balloon, how to calculate future value of an annuity, the beginning thing. Any problems that I'm going to pose to you, you're going to reduce them to those. That is mathematics. Mathematics is not arithmetic or algebra. Mathematics is taking a problem and reducing it to things you know how to do. And by following those steps, you can actually prove a lot of stuff. For example, 2,500 years ago, a little known guy, a Greek guy in Egypt, back of Alexander the Great, his name is Euclid. That guy proved that you could not write square root of 2 as a ratio of 2 integers. We call them irrational numbers, which means you can't write them as ratios. He made beautiful arguments as far as 2,500 years ago. I mean, today it's simple. You know, in proof theory, one of the first things you show is that. He basically is an interest in proof. I'm not going to go through the whole thing, but okay. We want to say that there does not exist a P and Q such that P over Q is equal to square root of 2. That's what the theorem is. But that's divorce E does where it exists. If I put a slash, mathematicians like compact notation. Now, this says you cannot find any pair of integers when you take that ratio is equal to square root. That sounds like a daunting task, but there are infinite many integers, and you're also doing a pair. It's infinity squared. So do I need to go through infinity square of integers one by one, even with a computer, to show that none of them has a ratio that's equal to square root of 2? He uses a very simple argument, which is common these days. It's called reductio ad absurdum. It's Latin for reduction to absurdum. We're going to assume that that's not true, and we're going to follow the logical consequences of that, and that's going to lead to something absurd. Okay? We always say, suppose not. Suppose there do exist, remember that. That means P over Q is equal to square root of 2, and assume that that ratio is irreducible. For example, 2 over 4 is reducible to 1 over 2. Right? And P over Q cannot be further simplified. If it could, then simplify it, and at some point you're going to reach with any ratio that it cannot be further simplified. Okay, if that's the case, square both sides. P squared over Q squared is equal to 2, right? That means P squared equals 2 times Q squared. That means P is even. Okay. Because only squares of even numbers are even. Think about it. Square of 3 is 9. Square of 5 is 25. So P must be even. Well, if P is even, then P is equal to 2 times K, some integer, right? So P squared is 4 times K squared. Or 2 times K squared equals Q squared. That means Q is even. Well, if they are both even, that means I can reduce that further. 2 over 4 is equal to 1 over 2. But I assume that it is irreducible. That's absurd. That means, assuming that statement is not correct, this is something absurd, hence it must be correct. That's mathematics. Okay? Using logic to reach conclusions. What things we use here? We use 2 things. We use only one thing that we knew about integers. That's if square of a number is even, the number must. That's the only thing we use. We took a seemingly horribly complicated problem, we reduce it to something very simple. If square of a number is even, the number must be. That's a fact. The number is 2 times another integer, it must be even. Those are 2 simple things we need. We can make similar argument to show that square root of any prime number is also right. It's a little bit more involved, but it goes along the proof of Euclid. Remember, this guy did this 2,500 years ago. Okay? There was no proof to it. He actually came up with it. Okay, he's a genius. Fine. And in ancient Greek society, if you were not doing geometry, you were nobody. And Euclid wasn't doing geometry. I guess after Alexander, things changed a little bit. But it's about mathematics. Reduce things to stuff you know how to do. Now I'm going to write down a very complicated retirement planning problem. If we did it algebraically, it would probably take 2 pages of algebra, depending upon how big your handwriting is. And we're going to solve it pretty much with 5 tricks using 2 times 2 times. Okay, let's write down the problem. You have $10,000 now. You will invest X dollars a month for 40 years, and you believe you can earn 0.75% a month on your account balance. That's kind of a reasonable number to earn after inflation. You invest into mid to large stocks, because that would be about 9% a year, roughly. Once you retire, you want to draw $5,000 a month for 25 years. But you want to leave 2.5 million to your grandkids. Or, when you're that age, you're gonna get yourself a 30-year younger girlfriend and leave the money to her when you die. Pick your stock. I don't know. Or leave it to charity. But when let's assume you're 20 now. When you're 85, you want your retirement account to show $2.5 million balance. And you believe you can earn 0.25% a month during retirement years. What is that $X that would help you achieve your goals? What you want is simple. Once you reach 60, you want a salary of $5,000 a month in addition to whatever you have, but just from this account. But when you're done, you also want $1.5 million in your account. And it's complicated stuff. Okay? But if you think about the problem, it becomes easy. Let's go to the end. I want to end up with $1.5 million. So essentially, transport yourself to age 60. You're going to have some money in your account. You're going to go to an insurance company or an annuity company and tell them, I want you to pay me $5,000 a month for the next 25 years, plus $1.5 million at the end of the year. What does that look like? That's an annuity with a balloon payment, right? And for that, I'm going to pay whatever that's in my account. So first, I'm going to figure out how much money do I need in my account at the time I retire. So at the time I retire, I'm basically buying $5,000 month annuity, 1/4% a month,